Okay, now we're going to change gears and talk about optimization. So at the cornerstone of all of neural network training, or even all of machine learning, is this idea of optimization across some data with some kind of model assumed inside of there. So we're going to talk a bit about how this is happening on the back end, the real nuts and bolts of the optimization engines, or at least one of the optimization engines that's commonly used to do this. This is out of this book here by Brunton and Kutz, section 6.4. You can find details on the book as well as more lectures, more source code. In fact, all the code that I'll present here is on this website, databookuw.com. Even though I'll be lecturing in MATLAB, there's Python equivalents is there as well. So I want to talk about optimization. In particular, I want to talk about gradient descent. Gradient descent is sort of the workhorse algorithm in optimization, especially for high-dimensional systems. Not even high-dimensional systems, but just in general as a tool for finding an algorithm to locate maxima or minima of functions. Over a landscape of something that you want to optimize over. So gradient descent is the workhorse. Gradient descent is ubiquitous across the sciences, just because it's a very generic tool. And one way to think about it is just simply in a high-dimensional landscape, how do you walk downhill? And that's what you want to do, is get to the global minima. And of course, gradient descent can't actually guarantee that you're going to get to a global minima, because you might get stuck in local minima, but we'll talk about that as we go along here. I'm going to walk through gradient descent, but I also want to talk about one of the more important versions of gradient descent that's commonly used, especially in neural network training, for very high-dimensional systems. So what we really want to talk about is stochastic gradient descent. So I want to talk about how stochastic gradient descent is connected to gradient descent, and then walk through a little MATLAB code to show you its implementation in practice. Okay, so as the name sounds, it's a version of gradient descent, and the part that we want to really understand is, what does it mean to have a stochastic component? So first, let's back up and let's talk about gradient descent. So typically in optimization, you are trying to find some function and to find a set of parameters so that you minimize some error, for instance. And so for instance, here's a generic representation of that. I want to take the argument of some error E, which is depending upon some different values of matrices A1 through A of M. Now, so I want to optimize over all those weights A of J. So the A of J's here are going to represent essentially the weights from one layer of a network to another. So here the idea is to have M layers, and each layer has a set of weights. So each layer's weights are called A1 or A2 or A of M. They're just a collection of all the weights. And so the idea, and what I've showed you before in the backpropagation lecture, which is the previous lecture to this, which is on section 6.3, is that you can frame this optimization problem as map an input to an output. And how do you map this so that you reduce the error? Find all the weights that minimize the error. So giving a training data set that takes you from a set of inputs to an output, and you have the labels correctly labeled, then find me all these weights, A of J's, so that some error is minimized. Okay? So that's it. That's the whole game. And the way these weights are minimized, or even formulating this objective function, I'll refer you to the backpropagation lecture, which will tell you how to formulate this practically given nonlinear activation functions going from one layer to a next. But let's just say that this is in fact what I want to optimize over, and so I got to pick all these weights. And of course, there's a high-dimensional space. There's a lot of weights to be picked out. In modern neural network training, these are extremely high-dimensional, and then you've got to figure out how to update all those weight values and walk downhill to some minima, and preferably, of course, a local minima, but of course, a global minima, but you can always get stuck in local minima, and we're going to talk about the stochastic gradient descent, which is going to help us out with this problem quite a bit, both in terms of making the optimization, much more computationally tractable, but also in terms of getting out of local minima because of the stochastic aspect of the search, gradient search. So here's what we really want to do. You give me a set of functions and weights. I want to take a mapping of a function f from an input x of k to an output y of k. So this is a generic representation. And remember that this function f would ultimately represent, from a gradient descent point of view, a compositional structure where you're mapping from one layer to another through some nonlinear function. And so f itself would represent some compositional framework. And backpropagation would tell us how to compute derivatives to minimize this. And so I want to walk over all the parameters, all the weights that I would have to minimize this error. So that's what's going to be how we are going to approach this from a neural network training perspective. This is the computation that's very costly in training. So training a neural network is expensive computationally because I have a lot of weights that I have to train over to minimize this. Okay? So that's the objective. In fact, normally I'd have n points, or n. I'd have a lot. I have to walk over all the data points through all the layers and all the weights for this thing. Okay, so suppose I give you a data set with, 1 million training samples with 1 million labels. So you're going to optimize this over all 1 million of the data set, okay, for all the weights. So that's a very large computation to do. And typically the way this is done is just with gradient descent. And we talked about gradient descent previously, which is I want to basically take my current vector of weights, let's call it x of j, walk it to the next set of values, x of j plus 1. And the way I'm going to do that is by updating the x of j and by including this gradient computation. So if f is my map from that takes me from an input to an output, then what I want to do is take the gradient of this map over those x of j, and then update it with some parameterization delta. Now, delta itself is what's often called the learning rate. So this is how much of a step in the direction of this gradient do you want to take to update your solution, okay? So gradient descent methods are basically trying to walk downhill. So at any point you are in space, you compute your local gradient, you walk downhill, and then the step you take downhill is determined by that delta. So this delta will tell you if you take a very large step downhill, which in a high dimensional space can be very, you can overstep and walk yourself over to a whole different regime, or you take a small little step in the right direction. But if you take really small steps, you could be optimizing forever because you keep taking very marginal steps down towards where the minima is. Okay? But in either case, that's the generic framework of gradient descent. With your error function, compute the gradient, walk downhill. And I showed you how to do this with a neural net when I talked about the backpropagation algorithm. You give me nonlinear activation functions between layers, and it will give you a way through backpropagation to compute this very easily. It's just chain rule. So that's important to keep in mind. You do a chain rule computation, and typically the activation functions are chosen so that they're very easy to differentiate. Again, I want to highlight something like the ReLU, which is piecewise linear. So doing the computation of the derivatives on a ReLU function, trivial. Just the slope of the ReLU function, and it's 0 on the left side. So, so you typically are picking activation functions so that when you do this high dimensional optimization, that this here is actually pretty easy to compute, even though you have to do a lot of computations. Now, typically what's done is you're going to evaluate your progress of your error by monitoring your error over all the data points. Okay, so in other words, my error, which depends upon the weights I've picked, is going to be basically the error over all the data points. So I really want to minimize it. So if I have 1,000,000 data points, it's not just how well did it do with one data point. It's I want to look and find to minimize this error over all the data that I have. So this n here is basically all the data that I have. Okay, where the e of k itself, remember, it is this function f, which is a composition, which is from an input x of k to an output y of k. And I just take the square of that error. So this here, we talked about in backprop, but now I'm going to put it in here, and I got to sum over all the data points. So I'm trying to find the weights so that given a large set of data, 1,000,000, 10,000,000, 100,000, whatever it happens to be, that what I'm going to do is find the best weights over all the data that's given to me. Okay, so this is very costly. Okay, but it does give you a global way to evaluate this over all of the data. That doesn't mean you won't get around local minima, but it does give you at least an evaluation metric over all the data. So the difference here between gradient descent and stochastic gradient descent is going to become now very clear. In particular, what stochastic gradient descent is going to do is going to say, how about this? Instead of computing my error and my weights over all of my data, I will compute this only over a single data point. So out of my 1,000,000 data points, I'm going to select one randomly, compute the gradient there. Now you can see how much this is going to be much more cost effective because I'm not going to have to walk over all 1,000,000 points. I might just pick one point, compute the gradient, make an update step. So here's the update of the weights. The weights currently, I compute this gradient and I get my next set of weights. Okay? So what I've done basically is with one data point, computing the gradient with that one single data point, I've given you a way to update and find a new solution or new set of weights, w j of +1. Now what's interesting about this, clearly it's not as good as using all your data. However, notice the advantages. First, computational cost. I'm only using a single data point. So I'm just going to use this, and of course there's also something bad about that, which is I'm only using a single data point. But computationally then, a single data point is going to be a lot faster than using all my data. Okay? Second, every time I update this, I randomly choose a new data point. So if I'm going to use this kind of structure, what I'm going to do is maybe I picked out of all my 1,000,000 data points, I picked the 500th data point, and the next time I pick 133,000th data point. So I keep switching which data I use to compute it as I update. Now what this is going to allow me to do is to randomly sample the space of the data. The hope being that in fact it's much harder to get stuck in a local minima because I am randomly walking around. So something that's a local minima for one data point is highly unlikely, or with very low probability, going to be a local minima for another data point. So by randomly subselecting data points, I can also more effectively walk around local minima to try to get to the global minima. So those are the advantages. And again, the disadvantages is that you're using a very small subset of the data with the hope that if I take many iterations, I can walk around local minima and down to some kind of global minima. Now, oftentimes you don't actually use a single data point, right? So this says, just take a single data point, which is the kth data point here, instead of all the data, just take one. So what people often do is take batches. So this is a common term used in training of neural networks, which is batch size, and that just is simply referring to how many data points do you want to take. I can take a subselection randomly chosen of k1 through kp points. So the point is this k here represents a selection of data, p of them. And I can now compute this gradient using p points instead of one point or all the points. So this is a way which can help frame this in a much better way, because instead of one data point carrying all the weight of what directions you take a next step. What you do here is you take a small selection, have them vote on which way is downhill. Take a step in that direction. Now what you do is once you've taken a step in this direction, you've updated your weights based upon the gradient computation of that randomly chosen batch, you now take another random batch, take another step. Another random batch, take a step. So notice the advantages you get in the stochastic gradient descent method. First, you've now taken this optimization to a much smaller optimization problem, right? So now, if you notice this, you're using P data points versus N, with the idea that P is really quite a bit smaller than N. So computationally, it's much faster. Second, by every single step picking a new batch, your ability to walk around local minima increases significantly. So now you're in a situation where you can essentially get yourself cost savings because you're doing a much smaller problem, but also you can avoid some of the pitfalls of gradient descent, which is getting stuck in local minima, because you're continually randomly picking different batches, and it's with very low probability that those random batches you pick would have the same local minima. So oftentimes you just walk right around the local minima down into something that's closer to a global minima. So this is the advantage. So stochastic gradient descent is, for those reasons, is sort of your workhorse architecture for doing large-scale optimization required of neural networks. So it's a very powerful technique, and it's just based upon standard gradient descent, which is just try to compute how to go downhill, which is through your gradient, and then walk that way. But now you're just doing it randomly with small selections of the data. So what I want to do is actually give you an example of this in a code here. And here's the code. So what I wrote is a little stochastic gradient descent algorithm for a very simple problem, and I'm going to show you the results of it. And you can play around with this. It's very simple to watch how this thing is actually working. So let's go here and let's start setting this thing up. So the beginning of this is very simple. I just define a domain. So, I'm an X and Y domain. So it's going to be a two-dimensional surface. My step size between them is 0.1, and I make a mesh grid of this. So my X and Y variables are a two-dimensional domain going from -6 to 6 and -6 to 6 in the XY directions. And I'm going to define a function f1. Here it is, which is 1.5 minus 1.6, some exponential, and I make my function actually be f1 plus some other exponential in there. So it's just basically two exponentials glued together. You'll see a picture of it in a moment. The main thing I wanted to show is that it had a local minima and a global minima, but that's it. There's this two minima in there, one which is local, one which is global. And so what we're going to do with this is we're going to say, from this surface, pick a point and see if I can do gradient descent or stochastic gradient descent to find the minima of this function. So every time I do this on this surface, I can compute a gradient over the whole thing. By the way, I can do that right here with this command, gradient of f. So that will give me the gradient over the entire spatial domain. Or what I'm going to do is randomly select a small set of values, compute the gradient like you would in stochastic gradient descent. So you do a draw of a small random set of values, compute the gradient, update that random draw, and keep walking downhill. So here's how it's done. Here is my random selection of points. I'm going to use the rand_perm command. So I take this thing, rand_perm of n. So in other words, my high dimensional state space is n dimensional. That's the function space, which is two dimensional, which has n values or grid points. And what I do is just take, I randomly permute them. And here, what I do is take the first 10. So my batch size is going to take 10 points, randomly from the surface, compute a gradient. Okay? So that's what I'm going to do here. That's what I've defined. I1 and I2 is just a random subselection of these points. And then what you can do is you can compute the gradient of these at these points. So here's the loop. And what it's doing for you here is computing, essentially, you take your function, and what we're going to do here is we're going to compute the gradient at these points, okay, at some randomly selected subselection of points. So I'm going to throw in these indices I1, I2 right into this here to produce a permutation of these things. So I'm going to, out of all the points available, take 10 at a time, compute a gradient, go through the loop again, take 10 points randomly, go downhill again, and just keep selecting out randomly 10 points. Okay. What I'm going to do here, this is tau. This is going to be my learning rate. So that's going to be my step size. Remember that the gradient descent says my future weights, or my future, whatever I'm trying to optimize, my future weights, or my gradient descent is going to say my future is equal to what I have now, plus a correction, which is the gradient plus times the learning rate. So the gradient is going to be computed here, and my learning rate is tau there. Okay, and then I just update. So at the end here, what I'm going to do is I just continue to update the solution. So once I find a new point, I overwrote the old ones, and then I update it, update it, update it. That's what this thing does here. Okay, and by the way, I stop here. So here's the computation of, by the way, this is the computation of the update of the solution and update of the derivatives for the gradient descent. And you can walk through this code a little bit more detail at your leisure, but the idea is very simple. You just walk through this, you have this very simple function, random down select 10 points, do the gradient descent. Okay, and if your error, in other words, if your weights are not updating by less than 10 to the minus 6, in other words, if you've converged to a set of weights, you break out of this loop, okay? And otherwise, you update your weights and you keep going through the loop. So let me just show you this. I'm going to run it, and you'll see what the figures look like. So this thing going through, and actually, let me move these over here. Okay. And here is an example of this, having run this, and these are both a top view of this and a bottom view. Okay, so there you go. So this is the landscape that I built. And notice I started here with this red, and it walked downhill, but of course it got into this local minima. So even though I did a stochastic gradient descent, this local minima is quite large. So to get out of it, you'd have to really take a much bigger, potentially learning rate, so that if I randomly moved very far away from this, I might get over this little hill that's here, separating this, to get over into the global minima, which is the blue. So by the way, so this is very common in gradient descent, is it's very easy to get stuck in local minima. And so what you need to do is when you get stalled there, you might want to search around or perturb away from it to see if you can still continue downhill. And there's other methods to do that, but right now this is just a very simple example of a stochastic gradient method search. However, if I start here, notice I just converge right down with the stochastic gradient method down to this minima. And there you go. This is now the top view of this, showing the convergence algorithms. And again, you can play with this very easily. We can change that learning rate to make bigger steps or smaller steps, and we can see what happens with those. So let's do this. Now I doubled the step size. And also where I started my initial condition. And again, you can start seeing that it converges much more quickly because I'm taking much bigger steps. Look at how big these steps are walking down that hill. Okay? Same thing here, but it's still not my random. I haven't chosen, I haven't been able to get out of this. This is a pretty hard hill to get over from that side to this side. But at least it illustrates for you a lot of the common features that you would see in a gradient descent, right? Which is this kind of structure, getting yourself to a global minima either through here or here. And remember, the advantage of what I just showed you is I'm not computing the gradient over this entire surface. Every time I take an update, I pick 10 points, and 10 points only. With those 10 points, I can walk down that hill. and get myself into one of the minima. So that's the main idea behind stochastic gradient descent. It's a really powerful tool, and one of the workhorses of modern neural networks is to think about this optimization process, which is extremely expensive. And instead of doing this gradient over all points, pick a batch size randomly, compute your gradient, take a step, pick another random batch, compute the gradient, take a step. Walk yourself downhill into some kind of global minima. So that's the main idea behind stochastic gradient descent. I thought it would be important for you to recognize that people have been very clever about thinking about ways to do this kind of optimization at scale. And again, for a neural network, you really have to think about how do you go to scale, because the number of weights in your systems is extremely high. Normally when we think about gradient descent, or even when you learn it in a class, you know, it's maybe you're doing 2 or 3 parameters gradient descent over it. Here we're talking millions, billions. It's a totally different ballgame. And so of course, lots of local minima, very expensive to do. And so stochastic gradient method really has these very nice features to be exploited that help you train a neural network in a better way, faster, with also some randomness in it so that maybe you'll get out of some of your local minima. So that's going to be it for this lecture. Now you have some idea about how stochastic gradient method works. And this is basically put onto the backpropagation architecture. And those two together form, let's call it the backbone or the dominant paradigm for optimization over neural networks. Certainly the rise and success of neural network was done on the backs of those two important ingredients, the stochastic gradient descent coupled with this backpropagation algorithm together so that you could actually train large-scale networks at scale. This is in this chapter 6.4 of this book by Brunt and Kutz. You can find more information here at databookuw.com. Lots of extra lectures that are there, and you can follow along there for all kinds of interesting things, as well as a code base. If you want to look at the notes for the book, here they are, databook.pdf off of that website, and you can download for yourself a PDF file with all of the information.